let's continue with our uniformly charged sphere problem. Our potential in the interior region is calculated as the integral from the reference point to the surface of the sphere, the radius r, and also the contribution from the interior part of the sphere. First term is just going to give me q over 4 pi epsilon naught r. And the second term gives me q over 4 pi epsilon naught r cubed, radius cubed, times little r squared over 2. That will give me, in turn, three q over 8 pi epsilon naught r minus q little r squared over 8 pi epsilon naught capital R. And written a little bit differently, I write it as q over 8 pi epsilon naught big R cubed and 3r squared minus little r squared. At the surface of the sphere, I should expect my potential to be continuous. And if I set little r be equal to big R, I will wind up with q over 4 pi epsilon naught big R squared. And that's exactly what I get from this side of this part of the potential expression. Okay? So potentials are continuous across boundaries. Electric fields, if you're talking about a conductor, are discontinuous across the boundary. In the case of a charge distribution, a uniformly charged sphere, for instance, that electric field will be continuous. Generally speaking, electric fields are discontinuous at boundaries. And that is your answer. Now, you may be wondering here, in order to figure out what the potential is, we had to know what the electric field was beforehand. And one of the arguments or advantages I put forth for calculating the potential is that you didn't need to do 3 components. Well, this seems to defeat the purpose of using an electric potential if we have to calculate the electric field beforehand. So I'm going to show you a different way of calculating the potential. I just showed you how to calculate the potential due to 2 charges. In one case, it's 2 like charges, and then a like and an unlike charge. And I mentioned that one of the features of potentials is that it obeys the superposition principle, much like the electric field and force. So we were able to sum up the contribution from each one. In the event that you have n charges, your potential becomes summation I equals 1 to n of qi, where I represents the ith charge, over 4 pi epsilon naught times the separation vector r minus ri. R again represents the field point or the observation point. Ri is the source point. If you happen to have a continuum of charge, in the same way that you could replace the summation sign with an integral sign when you were calculating electric fields, you can replace this summation sign with an integral sign. So therefore, your potential becomes 4 pi epsilon naught, the volume integral of the volume charge density divided by the separation vector, and now we're using the prime coordinates to indicate the locations of the sources. So that's what we're integrating over. If you happen to have a surface charge density, your volume charge density will be replaced by a surface charge density, and you'll integrate over an area rather than a volume. In the event that you have a line charge, the charge density becomes a line charge density lambda. Once again, generally speaking, is a function of r prime, all over r minus r prime, our separation vector. Now there's a huge caveat when it comes to using these equations. And the caveat is that these only apply for localized charge distributions. What do I mean by a localized charge distribution? I mean a sphere, cylinder of finite length, a wire of finite length, or a disk, for instance, or surface charge density, a shell. So any of those things are localized charge distributions. What is not localized is if you have an infinitely long wire, an infinitely long cylinder, an infinite charge sheet. All those things can't be used. What happens? Well, you wind up with an infinity. And as a rule, infinities are not a good thing. They are things to be avoided, generally speaking, not always. And you might be wondering to yourself, well, gee, have we discovered some fatal flaw in the electromagnetism framework? After all, why do we have to restrict ourselves to certain types of charge distributions? When I'm arguing, that's what the potential is. The answer there is that when you talk about infinitely long wires or infinitely long cylinders, those aren't real-world problems. You're never going to find an infinitely long wire in the real world. You're never going to find an infinitely long cylinder. We make those approximations because it makes for an easier problem to solve, and also if you have a very long wire, it can be approximated by assuming that it extends to infinity. So it's a useful approximation to make. It's just that there are certain restrictions. You have to be careful where you can apply those kinds of problems, and this is one of the cases. So you can't use this if your charge distribution extends to infinity, because you're going to wind up with an infinity here. Okay? So with that in mind, let's look at a few problems. The first one I'm going to do is a line segment. So I'm going to have a short piece of wire here. And I'm going to assume that my wire lies along the z-axis, and I want to figure out what's the potential at the midplane. Or what's the potential at z equals 0. So we've got a choice. Which of these expressions do we use? Well, it's a line charge, so obviously we want to pick the last one. And also we're tacitly assuming that our line charge is uniform, so therefore lambda r prime is just equal to lambda. And we're evaluating our integral at z equals 0, so r can just be written as s caret, or if you prefer to write it out with Cartesian unit vectors, this becomes s cosine phi x caret plus s sine phi y caret. And our r prime becomes, well, that's just along wire, so that's z prime, z caret. So now my potential becomes 1 over 4 pi epsilon naught. We're integrating here from minus L over 2 to L over 2. And I can pull lambda outside of the integral because it's uniform. And my integral becomes line integral from minus L over 2 to L over 2 of dz prime over s squared plus z prime squared. And my answer there for this is square root of s squared plus z squared prime minus z prime. And it goes from minus L over 2 to L over 2. And actually that should be a plus sign. And we'll have natural log out front. And our answer is lambda over 4 pi epsilon naught, natural log of square root of s squared plus L squared over 4 plus L over 2, all over square root of s squared plus L squared over 4 minus L over 2. And that is your answer for a finite wire. Turn again to our, I guess what's turning into our favorite system. We have a conducting sphere that bears surface charge density sigma. And once again, I want to figure out what is the potential. And I'll pull sigma out of the integral sign. So our r prime in this case is equal to r capital R sine theta prime cosine phi prime in the x direction plus r sine theta prime sine phi prime in the y direction plus r cosine theta prime in the z direction. And the reason why we're taking this r prime at the surface is because that's where the charge density is located. It's located at r prime equals r. And that should be a integral of the surface. Okay? Now what about where do we evaluate it? Well, I could write out an expression for all this stuff here, but I can remember that when we were doing the electric field problem, we made use of the symmetry of the sphere. In other words, we knew that whatever value the electric field had at a certain distance away from the center of the sphere, it had to have the same magnitude. And we assumed that also that it was going to be pointing radially outwards from the surface. So with that in mind, rather than trying to evaluate this at some arbitrary point and making our lives a little bit more difficult, why not simplify things and evaluate this along the z-axis? Just makes the problem a little bit easier to handle. Okay, Okay, so let's plug in these values here. And before I do that, let me calculate r minus r prime. So that's square root of the sum of the squares. We have big R squared, sine squared theta prime, cosine squared phi prime. We have R squared, sine squared theta prime, sine squared phi prime, sine squared phi prime. And then last but not least, z minus r cosine theta prime squared. So notice that these first two terms have in common factors of r squared sine squared theta prime. They also, first one has a cosine squared phi prime, second term has the sine squared phi prime. Let's make use of that vector or trigonometric identity that sine squared plus cosine squared sum up to 1. And multiplying this second term out, and notice my first term has a factor of r squared and sine squared theta prime, and the last term is r squared cosine squared theta prime. So using that same trigonometric identity, we wind up with r squared. So my separation vector becomes square root of r squared minus 2zr cosine theta prime plus z squared. So let's plug that in. We integrate over the thetas. That's sine theta prime d theta prime. So remember, dA prime is equal to sine theta prime d theta prime d phi prime, and r squared out in front here. Our second interval is 0 to 2 pi d phi prime square root of r squared minus 2zr cosine theta prime plus r squared, z squared. Okay, so there's no phi prime in the denominator, so I just evaluate that integral immediately. It just gives me a factor of 2 pi. It's useful oftentimes when you're calculating integrals using where you just have theta primes appear in either cosine or sine theta, they don't appear by themselves. And it's useful to make the substitution that u is equal to cosine theta prime, and therefore that du is equal to minus sine theta prime d theta prime. And that'll change the limits on the integral and flip them upside down, so we'll wind up with, instead of going from 0 to pi, we'll be going from minus 1 to 1. And this integrals is just nice and easy to solve. You don't have to look anything up here. Pull this constants out in front, so we'll wind up with the square root of r squared minus 2 zru plus z squared in the numerator, and we'll have to have 1 over minus 2z r times 1/2. So evaluating it at the endpoints here. We're left with minus sigma big R over 2 epsilon naught z times square root of square root of r squared minus 2zr plus z squared. I'm going to write this on the next line here so I don't go off the screen here. And minus square root of r squared plus 2zr plus z squared. First term, we have to write that as an absolute value sign, because we haven't made any assumptions as of yet whether z is on the interior or the exterior of the problem, so we don't know whether r is greater than z or z is greater than r. And the second term I can just write as r plus z. So in the event that we are outside the sphere, z is greater than r, have my minus sigma r over 2 epsilon naught z, and this would be z minus r plus z. And that gives me sigma r squared over epsilon naught z. It's useful to express this in terms of the charge Q. Now, again, remember, sigma is equal to 4 pi over r squared. And also, remember, I'm evaluating this on the z-axis for sake of simplicity. But I can generalize this to any r, because if I'm up here, the potential has to be the same thing as over here. It has to have the same value if you're equidistant from the center. So with that in mind, my potential outside goes as q over 4 pi epsilon naught r. Once again, we regain that same answer that we got knowing what the electric field was and then evaluating that line integral. And notice again, it's as if all the charge were concentrated at the center of the sphere. That's what potential you get. Now, in the interior region, r is greater than z, so my absolute value becomes r minus c in this case. So it's the r's that cancel out this time. I'll be left with sigma r over epsilon naught. But I know that sigma is just equal to q over 4 pi r squared. And that tells me that my potential anywhere inside of the sphere is equal to q over 4 pi epsilon naught capital R. This is a little bit less work than when we calculated the electric field, but it's still quite a few steps to get through, to go through to get a solution here. But again, when you have a conductor, well, in particular a spherical conductor, outside the potential is going to go as if all the charge were concentrated at the center. Inside this conductor, the potential is constant value. Now remember, when you had an electric field, the electric field vanished inside, okay? But potential is a constant value. And I should emphasize that's with respect to infinity. So in closing for our discussion on electric potentials, I'm going to give you a few homework problems to work on. So you've got a charged disk or a discharge if you prefer. And I want you to assume that your discharge or charged disk lies in the xy plane. You want to calculate the potential along the z-axis. Okay? So the question is, choose, first of all, which integral are you going to need? Are you going to use surface integral? Apparently so. And then what coordinate system will you use? And the answer there is sigma over 2 epsilon naught bracketed square root of z squared plus r squared minus z. For a uniformly charged sphere, we already worked this out. We already got the answer when we calculated it using the line integral of the electric field. But I want you to figure out what the potential is using those integral expressions. I want you to calculate the potential directly from the charge distribution. So in the exterior region, again, your potential should just go as q over 4 pi epsilon naught r. And in the interior region, remember your potential is not going to be constant throughout, and that's because your electric field is non-vanishing there, except at the very center. So the answer here is q over 8 pi epsilon naught big R cubed, 3r squared big R squared minus little r squared. And again, the only place the electric field vanishes is at the center. It doesn't vanish at the center when you're calculating the potential, but you will notice that at the boundary, these two expressions give the same answer because your potential is continuous across boundaries. And the last problem I'm going to give you, maybe I'll give you a couple of them. Let's say you've got two line charges. you to figure out what is the potential due to these line charges. So you're assuming that these guys are coming in and out of the board, and they're each located a distance a away from the origin, and your answer there is going to be lambda over 2 pi epsilon naught, natural log of the square root of x plus a squared plus y squared, and in the denominator of the argument of the natural log, you have square root of x minus a squared plus y squared. And the very last problem I'm going to give you is a little bit lengthy, so hopefully I will not make any mistakes when I copy this down. Let's say that you've got a uniformly charged cylinder. I want you to calculate the potential as a function of z. Okay, now let me read this off. If you're feeling ambitious, by the way, do this. Got some time to kill sometimes. This is rho over 4 epsilon naught, brackets, parentheses, z plus L2, L over 2, times square root of r squared plus z plus L over 2 squared in parentheses, minus z minus L over 2, times square root of r squared plus z minus L over 2 squared, plus r squared, natural log in the numerator of the argument. We have z plus L over 2 plus r squared plus z plus L over 2 squared, all over z minus L over 2 plus r squared plus z minus L over 2 squared. And then last but not least, we've got a final term minus 2zl. So that one is quite long, and as I said, it's easy to make a mistake. Hoping I copied everything down right, it looks right, but you always want to make sure your units look right and does it make sense, which will take you so far in electromagnetism, and then you just got to check and recheck your math. Okay. Well, anyway, thank you for joining me, and next time around we will be discussing boundary conditions, and we'll also be discussing some of the features of conductors versus insulators. And then we'll also, coming up as well, we'll have a discussion of how to calculate energy, potential energy, for electrostatics, and we'll see that's distinct from the electric potential.